Okay, good morning. Good morning, everyone. So in this presentation, we are going to talk about the challenges of synchronization, time synchronization in the telecom networks, starting from 5G, 5G advanced, going forward to the 6G world, and what is really required to ensure while somebody is testing those networks, what are the challenges of testing, what do you need to ensure that the time synchronization piece is working fine so that the other pieces of the 5G network can also fall into place. So this material, though I am presenting myself, has been prepared by me along with my friend Shahid from Cisco, myself product manager from Keysight for the network infrastructure test products, and Shahid is a product manager in Cisco for the timing and synchronizations. So we product managers, when we get tired of talking about our products, then we come on stage and start talking about technologies, right? Okay, so with 5G network, 5G advanced going forward to 6G, there are challenges in doing time synchronization. It requires time synchronization because of the different use cases that 5G exposes to the world. It's about the complexity of the technology and the modern application that modern application for different type of communication that 5G brings onto the world, right? So if we talk about the new use cases that came on with 5G, the first one that comes to mind is the URLLC or the ultra reliable low latency communication, which is again for industrial application for private 5G networks, where the endpoints which are connected over 5G, like it could be an autonomous robot working in an industrial plant, they need to have a time synchronous communication between themselves. So that requires time propagation over the 5G radio network towards the endpoints. Second use case that comes to mind is things like mobility or seamless handover when a car is driving, seamless handover for the user connected to the 5G network between the two cell towers, right? And then there are other use cases like proper use of resources, precise resourcing technologies where the base stations need to be connected properly, so that base stations need to be time synchronized properly, so that they can allocate resources dynamically. Now, amongst all of these, we will talk about the use case where we are looking at the radios, which are especially in the context of the seamless handover and the mobility use case, where the two radio cell towers, they need precise time synchronization. And this time synchronization comes from the network itself when the radios are connected over the front haul network with the base stations. So the industry has been developing radios and deploying radios with an architecture with time synchronization within 3 microseconds to support this type of use cases, but it becomes even more stringent, and the radios need to be in the range of a relative time error of less than 260 nanosecond when we go into the use cases of carrier aggregation or seamless handover within the radios within a cluster, right? So fundamentally, there are two ways in which this type of time synchronization is maintained in a 5G network. As we talked about, we are talking about the radios being in sync. These radios are connected over a Ethernet-based front haul network to the base station. Usually, in case of 5G, the base station either is the grandmaster or it has a direct connectivity to the TGM. Now, two aspects which are usually maintained. First is maintaining an absolute time error starting from the base station, or rather I should say starting from the source of the time, which is the TGM connected to the base station, all the way up to the radio, which is the end application. And in case of 5G, it has to be within, the absolute time error has to be within 1.5 microseconds. And the total time error, accumulated time error over the network path, if it is within 1.5 microseconds, two radios connected over the network path, their time alignment error becomes maximum 3 microseconds, which is required for the seamless handover part. The second aspect which is maintained in this network architecture is maintaining the relative time error of less than 260 nanoseconds, and these are for the radios which are within the cluster, they need to be within that range. So in order to achieve that, the way way we calculate how much time error budget is present for the network path itself, right? If we look at the total 1.5 microsecond that we talked about over the network path, usually the connectivity from the PRTC or the grandmaster to the ODU, which can be a physical device, which can be sitting inside a data center, is about 1 microsecond or 1.1 microsecond. That leaves around 100 to 150 microseconds for the rest of the network path between the DU and the RU. And for the relative time error, if we look at the calculation, the step one is we determine how much is the how much is the time error for the radio element itself inside the radio unit, right? Typically for a regular radio unit, it's in the range of 60 nanoseconds, and then we need to add also the time error for the UNI to that radio unit, the time for the radio itself, right? So after adding that, it becomes the total time budget within the radio unit itself becomes 80 nanoseconds for a regular RU. Now for an enhanced RU, where it is more efficient in terms of maintaining time, the time error budget comes down to about 35 nanoseconds. Now in order to calculate how much time error budget we have for the network path itself, we need to deduct this amount from the total time error budget. So if we deduct that from the 260 nanoseconds of total relative time error, this part, that gives us 100 nanoseconds for the network path. We are talking about two radios, so two network path, which means one link will have plus minus 50 nanoseconds of time error budget. For an enhanced radio, there is a little bit more leniency, and the calculation shows that it can be in the range of plus minus 95 nanoseconds of time error budget. So the networks, they need to maintain this, but what we need to understand also that between the DU and the RU, it's not a single link. There are multiple switches or multiple boundary clocks sitting in between these two functions, which needs to propagate the time. Now while propagating the time, each of them contribute to the whole time error budget by their own, by the time error contributed by the boundary clock itself. So while validating this type of architecture, what we usually do is we measure the total time error budget end to end, but at the same time, looking at this whole clock chain, we also need to attach to each and every point, rather maybe to all the boundary clocks, and then measure that which point is contributing how much time error to the whole end-to-end time alignment error. The test systems that can be used for this type of test, here we are showing one example of time sync analyzer from Keysight. So what it needs to have is an ability to have a clock reference from the time source, the TGM, and then an ability to take time reference from each and every point over PTP and compare them in the single system with reference to the clock reference that is coming from the source of the time. While testing, it is also important to test not only with PTP time references, but also with the signals coming over, let's say, 1 PPS. So the test system also needs to do needs to be able to compare the PTP reference, the 1 PPS reference at the same time for multiple points. So we have executed a test like this with multiple vendors, multiple popular vendors for the boundary clocks or the switches in the EANTC event earlier this year. Now, After the clock chain, the second thing that I mentioned is about the importance of validating the relative time error. Now, to validate relative time error, again the mechanism is very similar, but in this case what we do is a test port which is acting as a PTP time receiver replaces the radio units. So the time when the test equipment receives the time from the network, it compares all the time references within itself to calculate the relative time error with respect to the network time, which is again coming to the test equipment from the source of the timing, the TGM, as a clock reference. Now, one of the other things that we need to keep in mind is this network is not only propagating time. This network is propagating time because that's a supporting function for the actual work this network is supposed to do, which is to transmit the radio data from the base station to the radio unit. So this network will have a lot of background traffic while it is propagating time using PTP, and as we know that there are always chances in an Ethernet based network that a background traffic might impact a PTP packet, it might delay a PTP packet, and as a result there can be errors in how PTP calculates time. So this test needs to be performed in presence of background traffic. In general, it has to be realistic background traffic, which is in this case is a 5G traffic with radio data flowing through EC pre-encapsulation or the management traffic that is typically there in this type of networks. Like an year back or maybe year and a half, within Cisco and Keysight, we tried to do a POC in an O-RAN plugfest, and what we did is we built a network with Cisco switches and boundary clocks in a ring topology. It has a transport architecture designed by SRv6 microSID, and at the same time it ran time synchronization. So it's in a ring topology, had redundancy built in, and we tried to do a similar kind of test that I explained in my previous slides. What we found out at that time is that the relative time error we measured in that network was below 30 nanosecond, and we ran that test for two different scenarios, one with background traffic, one without background traffic, and we were able to achieve a below 30 nanosecond time error. Now, it's not only the timing part of it, like I mentioned, that there are a lot of other aspects that goes on into a 5G network. So I'll run the slide completely. What it says is that along with timing, there is the radio data going through the EC pre-encapsulation. In some cases, there can be TSN technologies applied. There are transport technologies like segment routing that gets into these networks. So it is important to test all of them in conjunction to make sure that things work in the reality. One of my previous speakers mentioned about Titanic sinking, and it's a similar case where until and unless we test everything together, we don't know whether things are going to work together. So that brings us to our last slide. The call to action to this group here is that all the 5G networks that we have seen, they are going to be virtualized, they are going to be sitting in data centers. So we need to make sure that the network and the compute architectures will work seamlessly to address the three things that are written on the slide: the resiliency, switchover, and security. Thank you.